Hey guys, welcome to video 6.2. In this video, we're going to be talking about the conservation of momentum. So we're going to start with reviewing a law that we actually have already learned about, the law of action and reaction. This is one of Newton's laws. And I just typed it out and kind of reworded it for you. It says that in every action, there's a pair of forces acting on two interacting objects. Okay, so here's two interacting objects. Here's a person pushing here, and here's a person pushing here, both pushing on each other. Okay, two objects. So there's a pair of forces. The size of the force on the first object, so here's our first object, okay, and this first object is pushing on this guy. So really I could draw his arrow like going this way. And then that's supposed to equal the size of the force on the second object. So this second object, this guy right here, is pushing on this guy, so I could have drawn it like this. But they're pushing on each other with equal amounts. That's the part that's really important. So if there's ever two objects that are experiencing a force, the force on the first object should equal the size of the force on the second object. The direction of the force on the first object is opposite the direction of the force on the second object, as you can see here. So forces always come in pairs in every single thing. So I'm going to show you a couple different examples of how force is affecting. So here's the club head of a golf club, and it's hitting the golf ball right here. So this club head is putting a force once they actually come in contact. So here is our golf club. Okay, try and draw it the same way that the picture draws it. So here's our golf club. Once it actually touches the golf ball, it's going to exert a force, a push force like this, an applied force on the golf ball. The golf ball, though, is also going to be pushing on the golf club with the same amount of force. The applied force that the golf ball pushes on the golf club is the same force as the golf club pushing on the golf ball. However, and you can see they're opposite, right? So the force that the golf ball's putting on the club is opposite that the club's putting on the ball. So these are opposite and equal forces. But just because they're opposite and equal forces does not mean that they have equal accelerations. Let's talk about acceleration for a second. The formula we're most familiar with is that the net force equals an object's mass times its acceleration. Well, if we were to rearrange this and solve for acceleration, we would get a formula that looks like this. We would say that the force of an object divided by its mass will give us the acceleration. So let's look at this formula here for just a second. Acceleration is due to force, which the forces should be equal on both objects, okay? So the golf club, here's the golf ball. Let's say the golf ball has a force and a mass if we wanted to find its acceleration. Let's say the club also has a force exerted on it, and it has mass. So what's interesting is that these are equal to each other. The forces are equal to each other, but their accelerations are not equal. Okay, these are not equal to each other, but the forces are equal to each other. So what does that mean? It means that their masses must be different. That's the only other thing in the equation that could give us a different acceleration. The golf ball has a much smaller mass, and the golf club has a much larger mass. So the acceleration is the movement, tells us the movement of the objects. So when the golf club hits on the golf ball moves much further than the golf club does, right? The golf club, in fact, doesn't even look like it moves backwards, right? That force that the golf ball puts on the club is so small and doesn't affect its acceleration. Okay, it basically doesn't have an acceleration because the golf club is so much more massive than the golf ball. So if an object has less mass, that force is going to have a bigger impact on it than if the object has a lot of mass. So let's look at these two billiard balls. So this rightward moving, the seventh ball right here, experience a leftward force, and the eighth ball is going to experience a rightward force when they hit. So here's this ball, and it comes all the way over here, okay, and it touches, it actually hits. So the seventh ball hits the eighth ball. So the seventh ball is going to experience a push backward because it hit the eighth ball. The eighth ball is going to experience a push forward because the seventh ball hit it. Okay, and so both of them have equal forces in opposite directions. Their movement might look a little different. If they both weigh the same and they both have the same mass, their acceleration is going to be equal. Okay, so they have equal masses and equal forces, so their acceleration's equal. But their accelerations are going to be in opposite directions. So this 8 ball is going to accelerate this direction, and this ball right here is going to accelerate this direction. Doesn't mean it's going to move that direction, it just means it's going to accelerate backward. Now, this 7th ball's velocity is forward. So what happens if you're moving forward but you're accelerating backward? It means you slow down. And we can tell that this 7th ball slows down, whereas this 8th ball speeds up because it's accelerating in this direction, and so it begins moving that direction. So since they're going the same direction, this 8th ball speeds up. Okay, so let's take that idea and let's apply it to momentum. Okay, so what we just said was that the force before is always equal to the force after. The force well, really what we said is the force are equal in opposite directions. Forces are equal in opposite directions. So the force 1 is going to be equal to the force on the other object. It's just in the opposite direction, right? So another way we can talk about that is the force before something happens is going to be equal to the force after something happens. Well, let's watch what happens. Let's say I have a baseball bat, okay, and here's a baseball. And the baseball is being thrown, and the baseball bat hits it. So once the ball gets right here, it's actually touching the baseball bat. The baseball bat pushes on the ball, and it makes a force applied forward. The ball pushes back on the bat with the same exact force, equal forces here, okay? They're equal forces. The bat has a lot more mass and it's being held by a person, so it doesn't go anywhere. That force doesn't have the ability to accelerate the bat too far, but the ball doesn't have anything stopping it, so it can accelerate much faster forward, right? So this one has a greater acceleration than the bat does. Well, we know that the forces are equal, so we kind of came up with this preliminary formula. We're not actually going to use this formula in problems. I just want you to understand the force before and the force after is the same. Okay. We also know that the time that it takes to actually apply the force is the same. So the time it took the bat to push on the baseball is the same time that it took the baseball to push on the bat, right? So the time that it takes to apply one force is the same time as it takes to apply that opposite force. So here's something kind of neat. We could combine those two equations to show this equation. The force applied on the baseball times the time applied on the baseball will equal the force applied on the baseball bat times the time applied to the baseball bat, okay? Do you remember or recognize this formula? You should. That's the formula for an impulse. Okay, an impulse is the same thing as change in momentum. So what we have just defined is how we can get a change in momentum before is the same as the change in momentum after. Also, the impulse before is the same as the impulse after. So what's the formula for change in momentum? Well, change in momentum is mass times the change in velocity. So what we can end up making is we can say that the mass times the velocity before is equal to the mass times the velocity after. So this is the formula really we're going to be sticking with and paying attention to, is this last one. So let's apply that. We're going to do some more mathematical stuff next video. In this video, we're mainly going to focus on concepts, okay? So I'm going to just give you an idea of what I mean about conserving momentum in a money situation. So here's Jack. He has $100, okay? Jill has also $100. So together, they have $200, okay? So think of this as being Jack's momentum. Jack has $100 of momentum. Jill has $100 of momentum. You can always combine momentums to find your total momentum, okay? Let's say after they collided, Jack gave 50 of his dollars to Jill. So now Jack has $50 worth of momentum. Jill has $150 worth of momentum. But together, guess what? They still have the same amount. That's what it means by conserving. We are keeping constant our total momentum. So momentum can only ever be transferred from one object to another. It doesn't just get lost, okay? So the conservation of momentum means that, you know, if Jack runs into Jill and he gives her some of his money, the total money is still there. Money can't disappear, just like, well, money can only change hands. So same thing with our law of conservation of momentum. Momentum can only change hands, okay? So Jack lost $50, Jill gained $50, but the actual total amount was conserved. So now let's look at it with a real momentum example. Okay, here's a cart, and it has like a brick on it, okay? And so it is moving, and so any object that's moving has momentum, right? Because what's the formula for momentum? It's mass times speed. So this has a certain amount of mass, and it has a certain speed. It has some sort of momentum. So they labeled it as MC, but I'm going to label it as PC because P stands for momentum. So this is the momentum of the cart. It has some sort of a momentum. In fact, I think they labeled it here. They have 45 units of momentum. Okay, so this guy's momentum is 45. Okay, this brick is not moving. So guess how much momentum it has? 0, right? No momentum. So the brick has 0. The loaded cart has 45. So altogether, how much momentum is present in this scenario? We have 45 units of momentum because we can just add the two together. So 45 is the total. Once we drop the brick onto here, the total momentum still has to be 45. Okay? Now, momentum, remember, is mass times velocity. So this cart now has gained mass, and so it's gained mass, it's going to slow down. And so that's what ends up happening here. After the collision, our brick now is moving forward with the cart, right? The cart's still moving forward. So this brick right here is still moving. So before it wasn't moving, but now it's moving. So its momentum went up, okay? And these are just made up numbers, but let's say it went up 14 units. So now this guy has a momentum of 14. Well, how do you know what the momentum is of this part right here, okay? Our original cart. Well, our original cart's going to slow down. So if it's slowing down, our momentum is also going to slow down, right? Because we know from that direct relationship that when velocity goes down, our momentum goes down. So if, let's say we didn't know what this was, let's say we didn't know that, well, we could easily subtract because we know that it has to equal 45 because our total momentums have to be the same. So I could say 45 minus 14. Whoops, I don't know what I was writing. 45 minus 14 will give us 30 whatever units, 31 units. So that is the momentum of the original cart. Let's look at another example. Okay, so a fullback and a linebacker are running into each other. Okay, let's say the fullback, he weighed 100 kilograms. Okay, and he's moving at a speed, so that's his mass. Let me rewrite that. Let's say his mass is 100 kilograms and his speed was 1 meter per second. Okay, let's say for the linebacker, his mass is 120 kilograms and his speed is the same. Okay, they're both going the same speed. Okay, so we would want to find out the momentum of the fullback and the momentum of the linebacker. Okay, separately, they're going to have separate momentums. So the fullback's momentum would be 1 times 100 because it's always mass times velocity, which gives us 100 kilograms times meters per second. So that's how we got this. And the linebacker's momentum is the same thing, m times v. So it's 120 times 1, which is 120 kilograms times meters per second. So which one has more momentum? Obviously the fullback has more momentum than the linebacker, okay? So this is what their momentum was before. So we have to add up all the momentum. So the momentum of the fullback plus the momentum of the linebacker will give me my total momentum. It's important that you add them together. So we have 100 plus 120 equals a total of 220. Okay, that's my total. After they hit each other, they're combined. So let's say the linebacker actually grabs the fullback, okay, and they're both falling to the leftward onto the ground. So they're combined now. So we want to find out what happens after they combine. So after they combine, oops, I need to do this here. Hold on. I actually made a mistake. I don't know if you noticed this, but the fullback has a momentum in a positive direction. The linebacker has momentum in the negative direction because it's moving to the negative place here. So momentum is a vector. The velocity of the linebacker was negative, so it ends up with a negative momentum. So we actually are subtracting these because this momentum of the linebacker is negative. So our total momentum is 20. Okay. After they hit, it wants to know what the momentum is. So after they hit, we have a combined mass of 220 kilograms. I got that because they're combined. So I just added the masses together. The mass of the linebacker and the mass of the fullback. I just added them together and I got that. Okay, so that's my total mass, right? So what's my momentum going to be after? Well, here's my mass, and it's mass times velocity. Okay, so I don't know my velocity, but they did give me my momentum after. So I could easily find my velocity by just solving for it. Now, what if they didn't give me, here's my velocity, so 20 divided by, no problem, by 220 will get you a number. That's your velocity. But the important thing is that you don't actually have to be given this. Why? Well, you know that the momentum before should equal the momentum after. So technically, if they gave you 20 kilograms on meters per second, then you know your momentum after should be the same exact amount. Here's another one. If we have a medicine ball that has let's say it's already been calculated. The momentum has already been calculated for the medicine ball. Before is 80. Afterward, and then it's going to hit a clown, okay, in the face. And the clown has a momentum of 0. He's not moving. What is the momentum after? They asked you to find that. Well, here's your momentum of the medicine ball plus the momentum of the clown equals your total momentum. Well, the medicine ball is 80 in the positive direction. The clown isn't moving at all. It's 0. So it means our total momentum is 80. Well, afterward, our momentum has to be the same. Okay, it can't change. So our total momentum here is still 80. And the reason why I can say, like, they combined, the medicine ball and the clown combined, they're both holding each other, so my total momentum is 80. Now let's do a couple more problems. I'm going to do two more problems, and this one's going to have a little bit of math in it. If a 5 kilogram bowling ball, so here's my bowling ball, is projected upward, okay, here's my bowling ball. It's got a mass of 5 kilograms and a velocity of 2.0 meters per second. Okay. What's the recoil velocity of the Earth? Well, okay, so here's the person who is throwing it upward, right? So if the person's throwing the ball upward like this, the ball is actually pushing back on the person, which is, again, then pushing back on the Earth with the same force. So the force here should equal the force here, okay? Unfortunately, we don't have force, okay? We have mass and velocity. So mass of the ball times velocity of the ball is, wait, we just do like 5 times 2. So the momentum of the ball is 10 kilograms times meters per second. That's the momentum of the ball. Okay. We know the momentum of the ball has to equal the momentum of the person pushing on the earth. So the earth is going to have the same momentum as the ball, because the momentum is always going to be the same, just like force is always the same. So the mass of the earth times the velocity of the earth should equal the momentum of the earth. The momentum of the earth and the momentum of the ball should be the same. Okay. So if I have mass of the earth right here, and if I have the momentum of the ball, which is the same thing as the momentum of the earth, then I can find the velocity of the earth. Velocity of the earth is going to be my momentum, which is 10, divided by my mass. When you put that in, you're going to get such a tiny number. Why are you getting such a ridiculously tiny number? Because the earth does not move when the bowling ball is thrown upward. The earth moves almost like a minuscule amount, like you can't even tell that the earth moved. Why? Because its mass is so big. Remember how we talked about if your momentum here is 10 kilograms times meters per second. That's a very small amount of momentum being applied to the earth. And because the earth is so massive, the velocity is going to have to be so small, right? Because they have indirect relationships. Okay, last question I'm going to go over is you should be able to describe the force, the impulse, the momentum change, and the acceleration in any kind of collision. There's a large truck, okay, and a little Volkswagen. Okay, they have a collision, they hit each other. The forces are going to be the same, right? The force is going to be the same. Which vehicle experiences the greater force? Neither. They both experience the exact same force. Which vehicle experienced the greatest impulse? Okay, what is impulse? Impulse is force times time. Do they both have the same force? Yes, we already talked about it. Do they both have the same amount of time that the impact is hitting on them? Yes. So neither. Both have the same impulse. What about momentum change? Well, momentum change and impulse are the exact same thing. So neither of them have a greater momentum change. They both feel the same amount of push. However, the only thing that's different is their acceleration. Acceleration is the force divided by the mass. They both have the same force. They don't have the same mass, right? The greater the mass, the less acceleration. Okay, so this car doesn't have a lot of mass, so it's going to experience a lot of acceleration. So this car is going to move this way, whereas your semi-truck is going to move only a little bit. It's going to have less acceleration, whereas your smaller car is going to have greater acceleration. And that kind of sums up everything that I want you to know from this video. The next video is going to focus more on the math aspect. This video is mainly just, I want you to understand the concept.
Whether it's a lineman stuffing a running back or a safety colliding with a wide receiver, all NFL defenders have a single-minded goal: to stop the ball carrier.
The object of making a tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact.
When a tackle is performed correctly, it's not just a thing of defensive beauty. It's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction law.
Newton's third law says that each action or force has an equal and opposite reaction. So if I were to push against the body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals mv. NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling.
It's very important to have some speed and momentum as you're going in to make that tackle. The better you're able to use that to your advantage, the better you're able to make contact and get a guy down right away.
In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, the momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's cradle.
In this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle three spheres.
The interaction of balls on a Newton's cradle can help illustrate what's known as an elastic collision, defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released, mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is, the energy of motion of two runners. After they collide, that energy is dissipated in deforming their bodies. That's like a spring. So some of your energy of motion went into that compression. You might have heard a loud snap from our pad. Some of the energy of our collision was transferred to the energy in the air that you hear.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress.
If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take him back. At the point of contact, hopefully that's where the ball stops playing in.
Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, we have Newton's third law to thank.